This is a video to support a course that I'm teaching on introductory proofwriting. And in the last couple of videos, we've looked at the notion of an equivalence relation and equivalence class, and we've tied together the notion of an equivalence relation and a partition of a set. So this is the last video that we're going to spend talking about equivalence relations, and we want to talk about maybe one of the most common equivalence relations on the set of integers, and that is congruence modulo n. But maybe before we do that, let's recall a couple of things. So R, which is a subset of A cross A, is an equivalence relation if it satisfies three properties. And I want to point out here that instead of saying the ordered pair x comma y is in R, we say x is related to y or x r y. So we have this first one, which is called reflexivity, and that is x is related to itself for all x in the set A. Next, we have this thing called symmetry, which says if x is related to y, then y is related to x. And finally, we have this thing called transitivity, which says if x is related to y and y is related to z, then x is related to z. So those three things make a relation into an equivalence relation. Next, we've got this notion of an equivalence class constructed from an equivalence relation. And that is attached to an element from the original set. So the equivalence class of an element x in A is given by the following. So the notation is this bracket around the x. Sometimes there are some other notations, but that's what we'll use. And that's going to be all y in A that are related to x. And I can put this in any order I want. I can put x is related to y or y is related to x by this symmetry condition up here. So this is going to be a set of a bunch of elements, and all of those elements are related to x. Okay, then finally, let's recall the notion of congruence modulo n. So if we've got integers a and b, and a natural number n, we say that a is congruent to b mod n if n divides b minus a. First up for this video is we want to show that congruence modulo n is indeed an equivalence relation. So that means we need to show that it satisfies these three properties. So let's just jump into it. So we'll check that it satisfies reflexivity first. So let's suppose that we've got some arbitrary integer. So I'm going to write this as we've got an a in z. And then I want to notice that we can write 0 as n times 0. But we can expand this out to say that this means that a minus a equals 0 times n. But this is the definition of divisibility. This means that n divides a minus a. But n dividing a minus a implies that a is congruent to a modulo n. Okay, so we've shown that congruence modulo n is reflexive. So now let's show that it is symmetric. So let's suppose that a is congruent to b mod n. And notice that that implies that n divides b minus a. But if n divides b minus a, that means that b minus a is equal to nk for some integer k. It's the definition of divisibility. But now we can invert this a little bit, and that's going to give us a minus b is equal to n times minus k. But if a minus b is a multiple of n, that means that n divides a minus b. But then n dividing a minus b is equivalent to saying that b is congruent to a modulo n. So that proves that congruence modulo n is symmetric. We started with a is congruent to b mod n, and we ended with b is congruent to a mod n. So now let's show that this relation is transitive. So we'll do that by starting off by supposing that a is congruent to b mod n and b is congruent to c mod n. Keeping in mind our goal is to show that a is congruent to c mod n. But let's unravel these two things via the definition. So this tells us that n divides b minus a and n divides c minus b. But now we can put those in terms of a multiplication statement. So this tells us that b minus a equals n times k, and C minus B is equal to, maybe we'll call it N times L. And this is going to be for some K and L, which are integers. But what can we do from here? Well, remember, we want something just involving A and C and then a multiple of N, but we can grab that by adding these two equations. So notice if we add these two equations, we can see that C minus A is the same thing as N times K plus L, where I factored an N out of the right-hand side. But this tells me that N divides C minus A, but N dividing C minus A is the same thing as saying that A is congruent to C modulo N, which was our goal for this transitivity property. Okay, so let's maybe get rid of this proof and we'll talk about the equivalence classes. So we just got done showing that congruence modulo N was an equivalence relation. That means it comes along with some equivalence classes. So let's work this out via an example. So maybe we'll set N equal to 5. So that means we're doing congruence modulo 5. Well, let's first find the equivalence class of the number 0. So by definition, that's going to be all integers b such that b is congruent to 0 mod n, mod 5. Okay, well, what things are congruent to 0 mod 5? Well, let's recall by the definition, that means that 5 divides b. So this is going to be all multiples of 5. So we could write this out as a list like this: 0 plus minus 5 plus minus 10 plus minus 15, and so on and so forth like that. The important thing about equivalence classes is that it doesn't really matter what equivalence class representative you take. You can have multiple names for the same element. So here we've got 0 is the equivalence class representative, but that's the same thing as looking at the equivalence class representative with 5. So the equivalence class of 0 and the equivalence class of 5 are the same modulo 5 in this case. And we proved a more general version of a statement like this in the previous video if you guys want to check up on that. Notice this is also going to be the same thing as the equivalence class of 35, and then so on and so forth. Okay, well, let's look at maybe the equivalence class of 1. So that's going to be all integers b, such that b is congruent to 1 modulo 5. Now we could play the game again where we write that as its definition. So in this case, 5 will divide b minus 1. But another really nice way to think about this is that b will have a remainder of 1 when divided by 5. So thinking of it like that, we can make a list pretty easily. So 1 and 6 both have a remainder of 1 when divided by 5. So does 11 and 16, and so on and so forth in that direction. Then if we move back in the reverse direction, we'll have like minus 4, minus 9, and so on and so forth. So those are going to be all the numbers that are congruent to 1 mod 5. And I want to point out that we could take another equivalence class representative as well. This is going to be the same thing as the equivalence class of 11, the equivalence class of 51, and again, so on and so forth. So it's not too hard to see that we're going to get 3 more equivalence classes in this case. We'll get the equivalence class of 2. So to write that as a list, it would be something like 2, 7, 12, up in that direction, and then minus 3, and then back in that direction. So that's going to be everything congruent to 2 mod 5. Notice some other things could serve as representatives, like 22. So the equivalence class of 2 is the same thing as the equivalence class of 22. Then next we could look at 3. So 3 is going to be on that set, 8, 13, 18, and then maybe back in this direction would be negative 2, and then so on and so forth in either direction. So this is going to be everything that has a remainder of 3 when divided by 5. We could take another equivalence class representative like 103. So the equivalence class of 103 is the same thing as the equivalence class of 3. Then finally, we have one more equivalence class, and that would be the equivalence class of 4. That's everything that has a remainder of 4 when divided by 5. So here we have 4, 9, 14, negative 1, negative 6 back in this direction. And then we could also choose an equivalence class representative if we wanted to. Like I believe maybe 99 would be an interesting choice in this case. Okay, so here's a specific example for n equals 5. Well, it turns out that often you'll want to think about these equivalence classes all as, put together into one set. And that has a name, and that's going to be Z5, which is just really the integer symbol with a subscript of 5, or in general with a subscript of n. Okay, so I want to clean up the board, and then we'll look at that definition precisely, and then something that we can do with that set. Okay, so we hinted towards this definition on the last board. Now we want to write it down very carefully. So Zn is going to be the collection of all equivalence classes modulo n. And so we could also write this in this kind of set builder notation. So this is the set containing the equivalence class of m as m runs through all of z. So in other words, every integer. But what I want to notice here is that this is like over listing the elements from Zn, which is fine because when you're making up a set, you can overlist the elements and you don't create a different set. So for example, the equivalence class of 0 is the same thing as the equivalence class of n, which is the same thing as the equivalence class of 2n, 3n, so on and so forth. That's because all of those numbers have a remainder of 0 when divided by n. Furthermore, the equivalence class of 1 is the same thing as the equivalence class of n plus 1, which is the same thing as the equivalence class of 2n plus 1, and then so on and so forth, because those all have a remainder of 1 when divided by n. So as you can see, we've got some overcounting happening here, which is like okay when defining the set, but it gives us some motivation that we can make a list description of this set Zn a little bit easier. And we could do that as 0, or the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, all the way up to the equivalence class of n minus 1. And all of those are disjoint. So in other words, this is a partition of all of the integers. So I want to go ahead and just remind ourselves really quick that this is going to be all integers m that are congruent to 2 mod n. This one is all integers that are congruent to 1 mod n, 0 mod n, and then going forward in the other direction. Okay, so I'm going to get rid of this, and then we're going to prove something related to the arithmetic of Zn. Next up, we're going to look at some of the arithmetic properties of Zn. And in fact, what we will prove is that addition and multiplication are well-defined in Zn. So what do I mean by well-defined, and why do we need to check that it's well-defined? Well, whenever you're dealing with equivalence classes, like you are in Zn, remember that's the set of all equivalence classes modulo n, something might go wrong when you take two different names for the same equivalence class and try to do something with them. So for instance, if we are in Z5, we know that the equivalence class of 1 is the same thing as the equivalence class of 6. So something that we would want to check, for instance, is that if we take any equivalence class, we'll maybe call it the equivalence class of x, and add the equivalence class of 1, we get the same thing as taking the equivalence class of x and adding the equivalence class of 6. So in other words, it doesn't matter which name you take for the particular element, you get the same result when you add by that element. Okay, so this is like a bit tricky and probably something that's kind of new, but this is a really, really, really important idea that you'll see like in an abstract algebra course as well. Okay, so let's maybe look at a proof of this. So we're going to start off by supposing that we have two pairs of elements in Zn, and those pairs of elements represent different names for the same equivalence class. So in other words, we're going to suppose that A, the equivalence class of A, is equal to the equivalence class of C in Zn, and the equivalence class of B is equal to the equivalence class of D in Zn. So these are perhaps different names for the same equivalence class. So I want to go ahead and point out that the equivalence class of A being the same thing as the equivalence class of C implies that A is congruent to C modulo N. So that's by the definition of our equivalence class is taken with respect to congruence mod N. And then furthermore, B equivalence class being equal to D equivalence class means that B is congruent to D modulo N. So there are two things that we need to check in order to know that addition and multiplication are well defined. So I'll maybe outline those here. So first off, we want to check that A plus B is equal to C plus D. Or the equivalence class of A plus B is the same thing as the equivalence class of C plus D. So, in other words, we can add using any of the equivalence class representatives and we get the same object. And then the second thing that we would want to check is that A times B equivalence class is equal to C times D equivalence class. So we can multiply with any equivalence class representative we want, and we get the same thing. So this is actually particularly useful when you're working, say, modulo 35, and you have to multiply by 38. So multiplying by 38 is quite difficult, but 38 is 3 mod 35, and multiplying by 3 is a lot easier. So this is the kind of time when you would maybe want to do a reduction and then use this fact that will prove. Okay, great. So what we really need to show is that A plus B is congruent to C plus D. And that's because two equivalence classes are the same if the two representatives are equivalent, but in this case that means congruent modulo N. Okay, so let's jump into it. So we know that A is congruent to C and B is congruent to D mod N. So that means we can write C minus A is equal to N times K, and then D minus B is equal to N times L, and this is for integers K and L. So I've like jumped ahead a step. Usually we write N divides C minus A, but we've looked at this several times already in this video, so I think that's okay. Now we can just add these two equations, and adding these two equations, we see that C plus D minus the quantity A plus B is equal to N times K plus L. But C plus D minus A plus B being a multiple of N is the same thing as saying that A plus B is congruent to C plus D modulo N. But A plus B being congruent to C plus D mod N means that the equivalence class of A plus B is the same thing as the equivalence class of C plus D. So we're good to go there. So next we want to check that multiplication is still okay, and we'll use this expression for C minus A and D minus B, but we'll rewrite it just a tiny bit. I want to write this as C equals A plus NK, and then D equals B plus NL. But now I can multiply those two, and I'll get C times D equals A times B plus N times K times B plus N times L times A plus N squared times KL. So that's what I get if I FOIL out this right-hand side. Okay, but now notice that I can rework this a little bit and write CD minus AB is equal to N times, well now we've got KB plus LA plus NKL. But the important thing is that it's a multiple of N. But CD minus AB being a multiple of N means that AB is congruent to CD mod N. But AB being congruent to CD mod N is the same thing as saying the equivalence class of AB is equal to the equivalence class of CD. So often you would write this addition and multiplication of equivalence classes as the addition of the equivalence class of A with the equivalence class of B, and then likewise on this side, C plus D. And what we checked is that this definition, where we bring the plus inside the brackets, is well defined. So that's in fact what we proved. And then furthermore, here we could have A times B, both equivalence class, and equivalence class of C times equivalence class of D. And here you say that you can bring the multiplication inside the equivalence class, and that's well defined. Okay, so I'm going to go ahead and clean this up, and we want to look at one last computational example. We're going to finish this off by looking at some computational examples of addition and multiplication in Zn for different values of n. So we're going to start with n equals 4, so that means we're going to be working in Z4. So just previously we proved that addition and multiplication was well defined. So that really brings us to this fact that maybe we could look at an addition and multiplication table. So let's maybe go ahead and do that. So if we do this addition table, well, that's not too hard. We can just add these two things in the brackets and that becomes our new equivalence class. So 0 added with anything is obviously going to keep it the same. So I can just put my first row and my first column down very quickly. So equivalence class of 0 plus equivalence class of 1 is clearly going to be equivalence class of 1, and then that kind of keeps going. Now let's do equivalence class of 1 plus equivalence class of 1. That's going to give us the equivalence class of 2. Equivalence class of 1 plus the equivalence class of 2. That's going to give us the equivalence class of 3. The equivalence class of 1 plus the equivalence class of 3 is going to give us the equivalence class of 4, but that's equal to the equivalence class of 0. Because if we divide 4 by 4, we get a remainder of 0. Now we can start filling in the rest. So here we'll have the equivalence class of 3. 2 plus 2 is 4, so that's the same thing as the equivalence class of 0. 2 plus 3 is 5. That's the same thing as the equivalence class of 1. Next, 3 plus 1 is 4, so that's going to give us 0. 3 plus 2 is going to give us 1 because we get 5, which has a remainder of 1 when divided by 4. 3 plus 3 equals 6, so that's going to be the same thing as the equivalence class of 2. Now let's see what happens with multiplication. Well, if we multiply anything by 0, we'll obviously get 0. So we've got the equivalence class of 0 in this entire row and column. If we multiply by 1, that will serve as something like the multiplicative identity. So here we'll get the equivalence class of 1, equivalence class of 2, equivalence class of 3, and then also down in this direction, 2 and 3. Now let's multiply by 2 and see what we get. So 2 times 2 is 4, but 4 is equal to 0 because we're working in Z4. Now that's pretty interesting because we've got these two objects, neither of which are 0, but when we multiply them together, we get 0. So that's how this does not act like the normal integers. Okay, now if we do 2 times 3, we'll get 6, but 6 is 2 mod 4. So we can replace that 6 with 2. Now we can fill in the rest pretty easily. So here we'll get this is 2, and then 3 times 3 is 9. But reducing that modulo 4 will give us 1. So looking at this, it's actually a pretty interesting question to see which of these elements have inverses and which don't under multiplication. Okay, now I'm going to have this other chart, which maybe I won't fill out all the way, just because it's fairly straightforward. But here we're working modulo 5. So I've got the equivalence classes mod 5, which are 0, 1, 2, 3, and 4. So let's pick some spot at random. So if we take 3 times 2, we'll get 6, but the equivalence class of 6 is the same thing as the equivalence class of 1. That's because we're working mod 5. Now if we go 3 times 4, we'll get 12, but the equivalence class of 12 is the same thing as the equivalence class of 2 because it is 2 more than a multiple of 5. Let's maybe do one more for good measure. We'll do 4 times 2. So 4 times 2 is 8, but 8 is going to be the same thing as 3 mod 5, so we can fill that in with the equivalence class of 3. Now, I urge you guys to fill in the rest of this chart if you need some practice, and that's a good place to stop.